So we can start. Don't forget that we are recording the meeting and to put in YouTube. And if you could please turn off your cameras and your microphones, okay? Thanks. Eduardo?
Okay, so it's a pleasure for me to introduce Umberto Hryniewicz, who works at the RWTH Aachen University in Germany. And he's going to talk about global surfaces of section and the conjecture of Birkhoff.
Thank you very much for the introduction. Can you hear me, just to be sure?
Yes, yes.
Okay. So before I start, I would like to say that it's a real pleasure and honor to participate in this celebration of Hildeberto. And for me, it's also especially a pleasure because of shared passion with selection mechanics with everyone here. So I'm very happy to be able to give this talk. Now I should try to somehow share my screen. I should click on present now, right?
Yeah.
Okay.
Acho que você tem que habilitar sua câmera primeiro, que nem habilitada tá.
Okay. So select, okay. Okay, now I think I have my camera.
You do.
Okay. Let me see if I can start over here. So present now. Allow. Share screen. I got a message saying can't share your screen. You must grant permissions in order to screen share. Maybe I have to be allowed to screen share. Será que eu tenho que ser autorizado a fazer o screen share?
Sim, alguém que está...
É Nete.
Marcelo?
Eu estou tentando aqui ver onde autoriza.
Deixa eu tentar de novo. Can't share your screen. You must grant permissions in order to screen share.
Marcelo deve autorizar 2 vezes, Umberto, porque tem 2 entradas.
Sim, mas eu não estou encontrando onde autoriza.
É o host que deve autorizar, né? Acho que é a NET.
O host é Marcelo.
O host sou eu.
O outro Marcelo.
Talvez o problema seja que ele está tentando usar a mesma ligação para fazer a apresentação. Teria que ser uma segunda ligação, né?
Então, como é que eu faço?
Se você tentar compartilhar do outro, ou então você passa para o outro dispositivo, assim, ele deve permitir...
Então, deixa eu sair e entrar de novo.
Pronto.
Boa ideia. We had some technological problems, but
Tá mostrando agora o slide, Umberto.
Aham.
Pronto, aí tu autorizou, Marcelo?
Sim, já está mostrando. Eu não cheguei a autorizar, não. Apareceu
Ah,
direto.
chegou aqui, pronto, massa.
Agora ele está sem áudio.
Agora estão me ouvindo?
Sim,
Sim.
agora sim.
Estão vendo minha tela também?
Sim.
Okay. Okay. Hello, everyone. Sorry for the technical. I don't know how to. I never use Google Meets almost, so try to not delay anymore. So, I mean, this is going to be a short talk. I try to fit it in the 40 minutes, and so it's a talk about global surfaces of section and a conjecture of Birkhoff. So the idea of a global surface of section is to study, a global surface of section is an object that allows one to study a three-dimensional flow, so a flow in dimension 3, by reducing it to a discrete system in dimension 2, by finding some kind of global, some section which crosses every trajectory infinitely many often in the future and in the past. So if you get such an object, you can reduce the study of the system to the study of the return map. So let me give you the definition. So here it is. So suppose you have a flow, I denote here by phi t on a smooth compact three-dimensional manifold. Just to be completely sure, are you listening to me? Is my audio okay?
Yes.
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 Sim, sim.
I won't stop anymore. So, right. So here, with the task. So the task here is to study this three-dimensional flow on a compact, smooth three manifolds, and a global surface of section is a smooth, embedded, compact surface with the following properties. So, first property is that the boundary consists of periodic orbits. And here it could also, I don't exclude the possibility of the boundary being empty. So I'm saying, okay, the boundary consists of a collection of periodic orbits. It could also be the empty collection or not. The flow is transverse to the interior. So it's not, of course, transverse to the boundary because the boundary is made of periodic orbits. Hence, the flow is tangent to the boundary. But in the interior, we ask the flow to be transverse. And the following holds for every point in the space. There are finite positive, negative times, such that if you flow the given point, you land in the surface sigma. You land in the global surface section. Okay, so it's some kind of section which is sitting in space in an appropriate way, in a suitable way, so that it cuts every trajectory in finite time, future and past. Right, so here's more or less a picture. I mean, you have some surface sitting there, the vector field generating the flow is transverse, and every point returns to the surface in finite time, positive and negative. And that's very good because when you want to study a flow, when you find such an object, then you can reduce the study of the dynamics to that of the return map, right? So you can imagine that you're sitting on a point in the surface, and then you flow for some finite positive time, you end up back in the surface. By transversality, this return map, time and return map are smooth objects. So you have a smooth diffeomorphism of the surface, And it's a diffeomorphism because you can also go back by assumption. Okay, so that's the definition of global surface of section. And please let me know if anything is not clear or if you have any questions. I cannot see the chat because I have full screen mode now, but please, if you just unmute yourself and ask anything you might want to ask, I'm glad to answer questions.
So, Umberto, why the periodic orbit in the boundary so fundamental?
Well, just because, so we want to have a surface, right? And a surface, if it has boundary, you want the boundary to be an invariant set because you want, say, the rest of the dynamics to be encoded by the return map. That's the idea. So you want the boundary to be invariant, but the boundary is a circle, so it's made of circles. It's a finite collection of circles, so you want the boundary to be an invariant circle. Is another way of, it's just periodic orbit. Okay. All right. So we are with this object. I mean, that's just a definition. This is just a tool. And why is it good? Because, well, the tools in the two-dimensional dynamics are much more well developed than the tools in three-dimensional, the tools for flows in dimension 3. And if you reduce the study of the dynamics to the study of the return map by such an object, then that's very good, because then you can apply the many results that are available for surface dynamics. Okay. So I should say, historically speaking, this concept, this idea, goes back to Poincaré, and I'm going to, or goes back at least to Poincaré, and I'm going to later say something about this piece of history. And in fact, this object was used by Poincaré to study the planar, circular, restricted three-body problem, and I'm going to explore that later in the talk. Okay. So one of the earliest, well, not as early as Poincaré himself, but almost, one of the earliest existence results, like, say, non-perturbative existence results for a global surface of section is the theorem of Birkhoff, which is pictured in this slide. The theorem is supposed to say the following with this. So I'm supposed to tell you the following with this picture. So here we are studying a geodesic flow on two sphere. Okay, so I'm looking at the geodesic flow as a flow on the set of unit vectors. So geodesic flow as a flow on the unit tangent bundle, right? So since it's a surface, the unit tangent bundle is a three-manifold. So we are in the situation of the previous slide. We have a flow on a three-manifold. And the curvature of this metric is assumed to be positive. Then the following is true. So here in blue, in the picture, you can see depicted in blue an embedded closed geodesic. These guys always exist. Embedded closed geodesics always exist. Actually, independently, if the curvature is positive or negative. That's a classical result to Lusternicke-Schneermann. So the theorem of Birkhoff says the following: if you have an embedded closed geodesic, then this divides the two sphere in two hemispheres. You choose one of the hemispheres and you place on top of each point of this embedded closed geodesic, you place a bouquet of unit circles pointing towards towards one of the hemispheres, towards the hemisphere you chose. And then if you let this bouquet of bouquet of unit vectors vary together with the base point, you get an embedded annulus on the unit sphere bundle, on the unit tangent bundle. Okay, so you see this bouquet of unit vectors. If you picture it on top of every point of the blue geodesic, you're going to get an embedded annulus on the space of unit vectors. And this annulus has boundary precisely on two periodic orbits of geodesic flow, which are the velocity vectors of the blue geodesic going in both directions. Okay, so it's embedded annulus. Its boundary is equal to two periodic orbits of the geodesic flow, just like in the previous slides. And the theorem states that if the curvature is positive, the every geodesic ray will change hemispheres. Every geodesic ray, which is not contained in the blue curve, will change hemispheres in finite time, infinitely many often in the future and the past. So in other words, the Birkhoff annulus is a global surface section. That's a nice result because, well, then you can use everything you know about annulus maps to study geodesic flows on positively curved two spheres. It's a very nice fact. And another nice fact about this result is that it is one of the few. So lately there has been some activity on this topic, but throughout the 20th century there were not that many results about existence of global surfaces of section on such situation, on such non-perturbative situations. So we see here we are talking about the positively curved matrix on a two-sphere, and that's a somewhat large infinite-dimensional set manifold of flows. This is not a perturbative result. Poincaré used also found annuli like global surface of section for certain regularizations, certain regimes of the planar restricted three-body problem. But in his situations, he was only talking about examining what happened as one perturbed from the rotating Kepler problem. So it was a perturbation of an integrable flow. And here, the contrast with the result of Birkhoff is that it's not. You just say the curvature is positive. Other than that, it's a very large set of flows. You can be very far from the round flow, for instance. You can be very far also from any surface of revolution. So please let me know if the statement of Birkhoff's theorem is not clear. And I just wanted to highlight that the nice thing about this theorem is that it's non-perturbative. Okay. So then, by the end of the 20th century, so I mean, during the 20th century, there were lots of works about global cross sections, which I didn't put here. There was that started with in the late 50s with Sol Schwarzman, who introduced the idea of an asymptotic cycle and proved some existence results about cross-section. But these results were only proved with certain assumptions which are hard to check. The same goes for the later results proved by David Fried and also by Danny Sullivan. I mean, there were some results which can be proved using basically, I mean, the theory of asymptotic cycles, which is like somewhat elementary too in ergodic theory. But these results were also, so to speak, not so flexible in the sense that these results came with assumptions which are hard to check, because in many situations one needs to check assumptions which involve large sets of embodied measures. These are hard to check. So then that's why I would like to highlight this theorem proved in 1998, published in 1998 by Hofer, Vysotsky, and Zander. And that's a very nice result because, so it states, let me just state the result. So the results are the following. Suppose you have a strictly convex energy level, right? So I'm talking about, I should say compact. So I'm talking about also here just the boundary of a nice, smooth, compact body sitting inside R4. And strictly convex here means that I just mean that the curvatures of the boundary of the convex body are positive. So I have this nice positively curved convex energy level sitting inside R4. Then every time you have such an energy level, the Hamiltonian dynamics on such an energy level has a disk-like global surface section. You can reduce to a two-dimensional discrete system by finding a disk, an embedded disk, spanned by one unknotted periodic orbit, and that disk is a global surface section. That's say comparable, given that it's 100, almost 80 to 90 years later than the result of Birkhoff. That's somehow, that meets some comparison, because here we're also talking about positive curvature, but it's a very different kind of positive curvature. And that's another big example of a nice result where the conclusions are on large sets of systems which are very, very far from being integrable, so non-perturbative result. Okay, so I will draw a picture of this result in a moment.
Umberto?
Yes, please.
I've got a question about the previous slide on that Birkhov's surface of section for the positive curvature. So why can't there be, for example, a hyperbolic geodesic in one hemisphere which is attracting the stable manifold prevents returning to the original cross section? Why is that not possible?
Right. So if I understand correctly, your picture, you're talking about some kind of little waste on one side, right?
Could be a waste. Or it's just it doesn't have to be a waste. Just a hyperbolic periodic orbit.
Right. So that's right. So if the picture in mind, is that of a waste, that waste would be, say, a local minimum of the.
Correct. Yep. But you can have hyperbolic orbits which are not minimum, right?
Right, exactly. So the picture of the waste is ruled out because the curvature, so that would be index 0 geodesic, and closed geodesic under positive curvature would have to have index at least 1.
That's right.
So now the picture, so if you don't have a hyperbolic orbits of index 0 sitting inside one of these sides, basically that's telling us that this cannot happen. Every hyperbolic geodesic is going to have to touch this blue. The moment the curvature is positive, and there are geodesics, I mean, you could imagine like a geodesic with even a orientation reversing index 1 hyperbolic geodesic, or an orientation preserving hyperbolic geodesic with index 2. This could be, but they just don't show up. That's what the result says. They just don't show up.
Okay, fair enough.
Okay. Thanks for asking questions, and please, anyone, I would like to keep it as informal as possible. Just ask some questions. Thank you. Okay. Right. So, right. So let me, before stating the result here, the second result in this slide, let me show a little picture. So our convex energy level is S3. S3 is R3 with a point at infinity. So that's the picture here. I'm trying to draw R3 with a point at infinity removed, S3 with a point at infinity removed. So this is the R3 you see in this slide. And the result of Hofer-Voskin-Zehnder says that if the energy level is strictly convex, then you find such a periodic orbit, which I drew in red. It's unknotted. The blue disk over there is our global surface section. So you should imagine that every single trajectory you hit this disk, every single trajectory is not contained on the red circle. We will hit this disk infinitely often, infinite time between hitting points in the future and the past. So you get a disk map. You get a disk map encoding the whole dynamics of the three-dimensional energy level. Okay, and in fact, you don't get only one disk, you get a whole foliation in the complement of this orbit by disks. So you see there is a whole one parameter family of disks. Each disk is a global surface of section. And these disks form the pages of what topologists call an open book decomposition. So that's the trivial open book decomposition of S3. Okay, every single disk is a global surface of section. So in particular, so there is the canonical example of why is this good is also an argument which is made by Hofer, Vysotsky, and Zander. So you can imagine in this picture, so maybe I should also say something. So these, we're talking about now a convex energy level in R4. R4 has the symplectic, the canonical symplectic form, the usual dq/dp from classical mechanics. If you see R4 as the cotangent bundle of R2. So it turns out that if you restrict this two form to this disk, to the blue disk, so you imagine that the blue disk is sitting on the boundary of this convex body. So if you restrict this two form, the symplectic form in R4 to the blue disk, you get an area form. Okay, this area form is a known-as area form in the interior. As you on the points of the boundary, it's not an area form anymore; it's degenerate. I mean, because the boundary is tangent to the dynamics, has to be degenerate there. But anyway, it's still a known-as area form in the interior, on the open disk, and it has finite area. Finite area because its area, by Stokes' theorem, is exactly the period of, say, the action of this orbit, the red orbit. And also, what turns out to happen is that the return map preserves this area form. So we have an area-preserving area for return map, so self-diffeomorphism of the open disk, preserving this area form, which has finite total area. So from that, we can apply Brouwer's translation theorem to conclude that the return map has a fixed point. And that gives a second periodic orbit. So you can imagine that the second periodic orbit given by a fixed point of the return map makes a Hopf link together with this together with the red orbit gamma. And so the complement of that fixed point is now an invariant open annulus, where there is also a well-defined return map, and it's also area preserving for some finite area form. So now we can invoke a result of John Frank's very strong result, which will tell us that as soon as you see some periodic orbits there, in this open annulus, the complement of the fixed points, you also find infinitely many periodic points. So here, for instance, this is the argument to prove using Hofer, Vysotsky, and Zander's theorem that in the convex energy level there are always two or infinitely many periodic orbits. So that's the canonical application of, so the canonical justification of why such a global section would be good for, at least from a theoretical point of view. Okay, so let me go back one slide. The second statement tells us that in such a situation, in a convex energy level, that we would like them to characterize which orbits span disk-like global surfaces of section. And these are exactly the periodic orbits which are unknotted, okay? So, of course, it has to be unknotted because it's supposed to bound an embedded disk, and has self-linking number -1. The self-linking number is some kind of it's one of the classical invariants of transverse knots from contact geometry, and its self-link number has to be -1 because the disk which is spanned by the orbit is transverse to the flow. That's so basically the self-linking number of a transverse knot has to be always at most equal to minus the Euler characteristic of the spanning surface. That's Bennekan's inequality, and in case you have a transverse surface, you have equality in Bennekan's inequality, and minus the other characteristic of the disk is -1. So then one characterizes, and then, for instance, the fixed point I was talking about here also spans another global surface section. So you have this system of these two systems of transverse foliations, and these can be used to further study the dynamics. Okay, so that's what I want to say about the global surface section. So maybe I should hurry up a bit. Time is running. Okay, so basically the goal of my talk was to talk about a conjecture of Birkhoff, which is already a conjecture made roughly 100 years ago, which talking about global surfaces of section. So it's a conjecture about global surfaces of section, and but the main point of my talk is to confess the failure of these symplectic methods to answer the conjecture. So, meaning people like me working in with symplectic methods are very happy to be able to prove results like this, which are very much non-perturbative. But the truth is that so far, to answer the question by Birkhoff, or to more say properly apply these methods in selection mechanics, for that goal, we are still basically failing, still not possible, at least not in a very satisfactory way. So basically, the talk today, the main goal of my talk today is to talk to you about the conjecture and how we cannot solve it. So let me move on. By the way, to a very nice book about this set of ideas, and that's basically where I learned most of the things I will talk about today, is a book by Otto van Koort and Urs Frauenfelder. It's a book which is exactly exploring this interplay between holomorphic curves and three-body problem. I should say, if I go back one slide, that all these disks, they are projections of holomorphic curves. So what happens is that the energy level is a three-sphere, and one can take the three-sphere and make the Cartesian product with R. So one gets this so-called that space R cross S3, the four-dimensional space. It comes with a special symplectic form, and these disks are projections of holomorphic curves which live on R cross the energy level. So this is really that's why here you see in the title of this book holomorphic curves. Okay, so let me describe the conjecture. So here you have the three-body problem. I mean, that's still not this planar circular restricted body problem. This is just the equations of the full three-body problem. I have three particles with masses m1, m2, and m3 in space, R3, and they have positions x1, x2, x3. So that's the system. So I need to explain three adjectives: planar, circular, and restricted. So restricted means that we are going to make m3 equals 0 on the first two equations, which means that the first two particles are going to move like solutions of the two-body problem, and we're going to cancel. So m3, of course, cancels from the third equation, which means that the third particle, supposed to be thought of as a massless satellite, is going to move under the influence of the other two, but it doesn't influence the other two. Okay, so we have this system, and the first two equations are independent of the third particle. So we are going to assume that the relative. So we know that the first two particles, they solve the two-body problem. We are going to assume that it's a circular solution, meaning that the relative position x2 minus x1 is a circular solution of Kepler's problem. That's what circular means. Planar means that the third particle, the satellite, is going to move also in the same plane as the first two. And restricted is what I already explained. We make M3 equals 0 in the first two equations and cancel M3 from the third. Right. So here's a picture. Here's the plane. The plane is the blue plane, and we have one mass. A little bit. I drew it in yellow. I mean, the slightly heavier mass. Maybe not so slightly, but okay, heavier mass yellow. The lighter mass is the blue, and the satellite is this purple. They move in the plane, the plane for me is going to be the complex plane. With a Galilean change of coordinates, we can make the center of mass at the origin. And the circular assumption is telling us that we have x1 equals to r1 ei omega t, right? So and x2 equals to minus r2 ei omega t for some fixed omega and some fixed r1 and r2, okay? That comes from the fact that the omega is constant, really, just because it's a circular solution of the relative position is a circular solution of the Kepler's problem. The third law of Kepler tells us that there is a relation between omega, R1, R2, M1, and M2. And so here's the system, right? We have these, zeta is the relative position for the first two. So we have you see that here that it solves the, can you see my mouse here? Solves the Kepler's equation. And then the algebraic miracle is that if we introduce now a non-inertial coordinates by, you see, we make the relative position between, say, the satellite and the mass x2, and we put some, say, a rotating coordinate system, so we rotate back by this multiplying by e to the minus I omega t. We get a new variable q in a non-inertial coordinate system. It solves this second order ODE right here. And so the miracle is that if one introduces this strange momentum p, we have a Hamiltonian which turns out to be time independent, right? So that's the algebraic, say, surprising fact that one starts with an equation for the satellite, and the terms of the equation are depending on the time, but because the solution is circular, after one does this reduction, one ends up with an autonomous Hamiltonian. Right, and this parameter mu here is the mass ratio. Okay, so that's the Hamiltonian, and then we are going to look at regimes where so there are two parameters here: the mass ratio mu and the actual value of the Hamiltonian h. We're going to look at subcritical energy levels. Okay, so we're going to look. This Hamiltonian h has 5 critical points and 4 critical values. We're going to look at energy levels below. It varies from minus infinity to plus infinity. We're going to look at energy levels below the first critical value. And there, the projection to configuration, to the configuration space of the energy level for such subcritical regime is this, this green region, which these are the 3 Hill regions, so-called 3 Hill regions. We have 1 Hill region around each massive body, and you have also an unbounded Hill region, a neighborhood at infinity. And the satellite is confined to move in one of these. So we're going to look at the satellite in one of the bounded Hill regions. Let's look at the satellite near the yellow mass. Okay, so that's the task that Birkhoff was looking at. And so here's the picture again. Here is the Hill region. The satellite's moving there near the yellow mass. We're still subcritical, which means that the Lyapunov orbit was not yet born because we're below that energy level. So the satellite, the Lyapunov orbit was not yet born between the masses. So the satellite is moving inside that Hill region. Okay. Are there any questions about the equations or the problem? Please let me know if there are any questions, if something is not clear. So, okay, so the question is, given, and that's also maybe a question I have to you, because I'm not a super specialist in this topic. Is it known that given a subcritical energy level and any mass ratio, so that's what I would like to stress here, any mass ratio, so we're not talking about mass ratio close to 0 or close to 1, we're not talking about special choices of energy, so we're not talking about energy close to minus infinity or anything like that. Do we know that for a subcritical energy value and any mass ratio, is there always a direct orbit? That's the question. As far as I understand, in this generality, the question is still not proved, or at least not proved without computer assistance. I think not even a computer assistant proof is available, maybe. Of course, there are many instances, many values of the parameters, energy and mass ratio, which are understood. But I think in general, in such generality is not known, and that's the original question addressed by that Birkhoff wanted to study. So let me go back one slide just to tell you, just recall what's direct orbits. Okay, so let's look at this picture and suppose that our omega was positive. Okay, so this means that before we introduce our non-inertial coordinate system, these massive bodies were moving, say, in the positive direction. So we have to introduce this. So now we're introducing the non-inertial coordinate system means that we rotate together with them. And then we can now talk about orbits which go around. So periodic orbit which goes around, and the important word here is the adjective periodic. So a periodic orbit which goes around, say, the yellow mass in the positive direction will be called direct. Okay? Why? Because I'm thinking that my omega was positive. Of course, if my omega was negative, then I should call direct orbit something that goes in the negative direction. But so I want to call direct a periodic orbit which goes around the yellow mass in the same sense as the rotation of the massive bodies. That's a direct orbit. And a retrograde orbit would be exactly the same. One orbit, periodic orbit, which goes once around the yellow mass, but against the sense of rotation. So that's what I mean by direct and retrograde orbits, periodic orbits. And okay, so I guess all this time after the start of the planar circular restricted three-body problem, I think we still don't know really that, maybe I'm wrong, but I think we still don't know really that there is always a direct orbit for any mass, subcritical mass, any subcritical energy level and any mass ratio. Okay, of course, there are many known results. For energy values close to minus infinity, that was, I guess, the PhD thesis of Charles Conley. Well, not really, but I mean, Charles Conley proved that for energy levels close to minus infinity, one has a pair direct retrograde orbits, and this pair of orbits are elliptic. Well, they for sure are. If I remember correctly, they for sure are spanning a return. So spanning an annulus-like global surface section, for which the return map satisfies the twist condition of the Poincare-Birkhoff theorem. So that's why Charles Conley was able to, I think, his PhD thesis to get infinitely many periodic orbits on those energy regimes. Please correct me if I'm saying something wrong, but I think that's right. So for mass ratio close to 1, let's say mass ratio is the mass of the yellow divided by the total mass. So this means that mass ratio close to 1, if I go back one slide here in this picture, that would be exactly the rotating Kepler problem. So for mass ratio, say exactly equal to 1, so you think of the blue particle now with 0 mass, all the mass is concentrated in the yellow particle. So the Hill region around the blue particle goes away, fades away. The Hill regions, the other two circles, the boundaries of the other two Hill regions, they become now concentric circles around the yellow mass. And inside there, you see in the bounded Hill region, you would see the projection of the dynamics of the rotating Kepler problem, which has two periodic orbits, direct and retrograde. And Poincaré basically invented the continuation method to prove that these orbits persist if you perturb the mass ratio a little bit below 1. And in fact, Poincaré was able to argue that these orbits for mass ratio close to 1 also span an annulus-like global surface section. And that's actually the reason why Poincaré stated his last geometric theorem. Poincaré was thinking about this return map on that annulus when he was thinking about the what would be later called the Poincaré-Birkhoff theorem. Another situation where we know something is mass ratio close to 0, which means that now we would be talking about what happens near this very small Hill region. I mean, suppose that now we're talking about the mass almost completely inside mass almost completely concentrated in the yellow, but now we want to study a satellite near the blue. In those regimes, one can still explode the coordinates in a suitable way and still get the global surface section there. Also, one can also get the direct and retrograde orbits. But I guess in general, we still don't know how to answer the existence of a direct orbit. By the way, Birkhoff already proved that the situation is much better for retrograde orbits. So Birkhoff developed the so-called Birkhoff shooting method to prove that yes, one always has retrograde orbits. Okay, so it's a very nice result. But for direct orbit situation is much more complicated. So here's a conjecture I would like to talk about. It's found in this paper by Birkhoff from 1914. So the conjecture is actually just part of a strategy to get the direct orbits. Okay, so let me just read what Birkhoff wrote, and then we can discuss it. So the statement is the following. At some point in the paper, Birkhoff says, this state of affairs seemed to me to make it probable that the restricted problem of three bodies admit of reduction to the transformation of this coin into itself, as long as there is a closed oval of velocity, of zero velocity about J. J was, say, one of the masses, one of the heavy masses, and that in consequence, there always exists at least one direct periodic orbit of simple type. So in other words, Birkhoff's strategy was the following. One takes such a subcritical situation, okay? One looks at retrograde orbits, which he knows exist. One tries to find a disk-like global surface section spanned by the retrograde orbit. And here it's good to keep a little bit free how you regularize the problem. You might want to look at Levi-Civita regularization, or maybe after Moser, you can talk about Moser's regularization. So in any regularization, one would like to, or maybe one needs to invent a new regularization. In any regularization, one has to, the strategy is to take the retrograde orbit, do something, try to prove that it spans a disk-like global surface section, and then hope that the fixed point of the return map, which exists by Brouwer's translation theorem, is going to be a direct orbit, or some kind of, say, reasonable substitute for the direct orbit. So that's the conjecture. That the conjecture perhaps in more modern terms, would be that, okay, there's got to be, for subcritical energy levels and any mass ratio, there's got to be disk-like global surface section spanned by a retrograde orbit, and then we can hope to use the fixed point to get a direct orbit. Annette, I had 40 minutes, right?
I think it's 50 minutes for the presentation.
Okay. How much time do I have now?
Well, that's probably not much.
Okay.
Finish up.
All right, because I remember we started at 3:20 or 3:25 or something like that, which would mean that now it's 40 minutes, so I can stop now.
No. I guess you can go on for about 10 more minutes.
10 more minutes? Really? Okay. I don't want to go too long. But yeah,
Well,
I have more. I just don't want to overuse the time. I'll just show a couple more slides then. Okay, so here's the conjecture, which is supposed to be part of a strategy to find direct orbits. And basically the situation is that for energies close to minus infinity, or for energies which are subcritical but with mass ratio close to 0,1, yes, we can solve the conjecture, but that's a bit of not satisfactory, because in all these situations, for energies close to minus infinity, or from me close to 0, or from me close to 1, in all these situations, one can always reduce to a perturbative statement. One can always reduce to a situation where one is perturbing from an integrable case, where everything can be done by hand, which means that the true difficulty in answering this conjecture is to handle arbitrary mass ratios and also arbitrary energies, subcritical. Okay, so that's the conjecture. Okay, so here are some questions which would be very much related to the conjecture about retrograde orbits. So first question is there a retrograde orbit with minimal action? I wrote here period, but here better word would be action among all periodic orbits. Because if that's the case, you see, I mean, in any kind of regularization one does, for instance, if one does Levi-Civita regularization, one lifts the flow, one compactifies the flow to a flow on the 3 sphere, and there, so one has to double cover the retrograde orbit in order to get a periodic orbit on this lift, and this orbit, the double cover of the retrograde orbit under Levi-Civita regularization is unknotted with self-linking number -1. Okay, so which are the good properties of the orbits, as we saw before. So if this orbit would have minimal action, then yes, one would get compactness, that the compactness one needs from the holomorphic curves to span that open book with disk pages, which are all global surfaces of section. But I guess this question, I think the answer may be still not known. So another question is the retrograde orbit linked to all other periodic orbits? If that question would be also have is some retrograde orbit linked to all other periodic orbits? If such a question would have a positive answer, then also one would be able to get the disk-like global surface section required by Birkhoff. Another related question, which I also maybe ask the audience. I mean, inside the bounded Hill region for subcritical energy values and for arbitrary mass ratio, is the retrograde orbit unique? That also, I don't know, and that would be very important. I mean, anyway, I think it would be nice to know. Maybe the answer is not, it's false. I mean, but I'm just put it here because then somebody knows the answer, I can also learn. I'll be very happy to. Okay. Here's the picture for the mass ratio close to 1, which means the picture I mentioned before. The blue mass disappears, fades away. All the heavy is here on the yellow mass. The boundary of the Hill regions which survive are these concentric circles here. And inside here you find a retrograde and direct orbit, very nice embedded circular orbits. These are orbits found by, I think, maybe first by Poincaré. And these guys are, except for very exceptional values of the parameters, these orbits are going to be elliptic. And so they're going to persist when mu is perturbed away from 1 a little bit. And these guys are also going to, for this perturbation scheme, these guys here on this for the rotating Kepler problem, these are spanning annulus-like global surface of section, and for mu close to 1, this would still be the case, and so that's how Poincaré applied his last geometric theorem. Here below, you can see the formulas for the Levi-Civita regularization. It's a 2-to-1 set of coordinates, which means that now every point in phase space is represented by 2 pairs, UV, in C2, which are antipodal symmetric. So actually one lifts the flow to a flow on a 3-dimensional energy level, which is diffeomorphic to a 3-sphere, but it's actually antipodal symmetric under the antipodal map. Here's just a picture of kind of the lift of the retrograde and direct orbits on the Levi-Civita regularization form a Hopf-link, and here's kind of the picture of how Poincaré's annulus look like. And here is the statement of Poincaré-Birkhoff theorem, just to tell you how. So Poincaré checked the twist condition for mu close to 1 for perturbations of the rotating Kepler problem. Okay, the pendulum tells us that the Poincaré-Birkhoff theorem is optimal. And okay, here's my final slide, just to tell you how it looks like if you look at the complement of one of the orbits as a solid torus, kind of this twisting annulus, which is bounded by these core blue orbit, and the other orbit, the purple orbit on the boundary, these are the Hopf-link, and the Poincaré's annulus is like this helicoid-like annulus surface. Okay, I think I'll stop here. Thank you.
Yeah, I can't, but anyways, thank you very much, Umberto, for the talk. Very interesting. It was really interesting. Also, I recently came across the book you mentioned, the Frauenfelder book, I think, and
Otto von Korn.
And I don't remember the second book, maybe, but very interesting book. Yes, indeed. I really liked it. I hope the exchange rate doesn't get too bad soon. But anyways, so are there questions for Umberto? Anybody would like to ask any questions?
We have a question.
Can you hear me?
Yeah, Bob.
Oh,
hi there. Umberto, thank you very much for your presentation. Very interesting.
Hi.
I wonder if you could say something about the stability of this periodic orbits. Can you hear me?
About it was a little, it cut the audio.
Hello, can you hear me?
Not, yes, now I can.
Yeah, that's the thing. So I was talking about the stability of the periodic orbit vis-a-vis small perturbations.
Yeah, the periodic orbits one gets for perturbations of the I mean, if you have the rotating Kepler problem, which is the new all the mass concentrated in the heavy body around which the satellite moves, in that case one gets these two circular orbits, the retrograde and direct ones, and Poincaré, Poincaré checked that these orbits, except for I think very exceptional cases of values of mu and energy, these orbits are elliptic irrational. So that's why they persist if you perturb mu a little bit. And I'm not sure about what can be said with respect to KAM theory, but I think also for most of the values, the tori, because the rotating Kepler problem is integrable, and I think also that, maybe I'm mistaken, but I think also except for a very exceptional set of values, the many, you can apply KAM and you get many invariant tori. But these are all perturbative results, and yeah, Birkhoff's conjecture is really a non-perturbative conjecture.
Thank you.
okay. Other questions? All right. Well,
can I ask the second one? You can be quiet.
Yeah. Anybody wants to ask any more questions? Well, let's thank Umberto again, Ben, for his talk. I think that's about it, right, Annette? I did not receive any more information about.
Now we have the happy birthday Hildeberto today.
Oh yeah.
Yeah.
Okay. You take over.
Could you see?
You take
Olá, Hildeberto, feliz aniversário. Queria dizer que é com imenso prazer, né, que eu participo dessa comemoração em homenagem aos seus 80 anos. E queria lembrar um pouquinho como foi que a minha trajetória cruzou com a sua, né? Em 95 eu fui fazer mestrado na UFPE e eu queria fazer álgebra, mas acabei fazendo uma disciplina de análise RN com você. E com isso, como as suas aulas sempre estavam muito permeadas de geometria e história da matemática, eu fui me encantando, né? Me apaixonando pela análise, pela geometria, né, pelas equações diferenciais e depois pela mecânica celeste, que você sempre trouxe de uma forma muito apaixonada, né, essa área. E aí queria dizer da minha admiração pela sua trajetória, porque sempre foi uma trajetória de muita união, né, de buscar pessoas, de colaborações, mas não só colaborações, né, com o objetivo de produção, mas uma colaboração também com muito afeto, né, sempre unindo as pessoas. Aí outro dia a Cláudia até mandou uma foto do encontro na UFAL, que a gente fez aquela aventura da viagem até Maceió, e aí eu mandei para a Cida e ela disse assim, ai, que saudades daqueles tempos, e realmente tempos muito bons, né, de muito aprendizado e de muita conexão. Então, queria agradecer por todos os caminhos que você abriu para mim, não só para mim, mas por todas e todos que estão aqui, né? E queria terminar lendo aqui um soneto seu, espero que eu faça a altura, provavelmente não, mas vamos lá. Então, é um soneto que você enviou faz tempo para vários de nós vários, né, coisas que você escreveu, e esse se chama Nociva Regularidade. Vazio absoluto de plena regularidade, pleno de formas, de sons, de cheiros e de cores. Não falta plenitude em todos os setores, e então tudo é vazio por sua uniformidade. Como a variação se torna uma necessidade no humano universo quando fruto de labores, linhas de montagem que só causam dissabores, ao reduzir tudo a padrões com pouca variedade. Em contraste, a natureza equilibrada e infinita nos mostra a beleza da diversidade. Não só a beleza, mas também estabilidade. E ao ser ferida pelo homem, não hesita em mostrar sua força ao arrogante, reduzindo a uma escala humilhante. Então, obrigada por tudo que você nos ensinou, gratidão, e quero desejar mais uma vez parabéns e agradecer pela oportunidade de estar aqui. Parabéns também à organização do evento, né? E feliz aniversário, Hildeberto, muita vida pela frente. Parabéns também a Elizabeth e a seus filhos, né, por conviverem todo esse tempo com você. Um beijo.
Pode parar a gravação.